Okay, for the second set of notes for Unit 2, we're going to be talking about nuclear chemistry. And nuclear chemistry has to do with, obviously, the nucleus. That's why it's called nuclear chemistry. So it's all about the structure of the nucleus and how the nucleus changes. Now, nuclear reactions are different from chemical reactions. When we're talking about nuclear reactions, we want to remember that it happens when the nucleus either combines with another one, splits apart, and gives off radiation. It can involve protons, neutrons, and electrons. It is associated with large energy changes. And what you're going to see is atoms of an element are often going to be changed into another element. That doesn't happen in a chemical reaction. And nuclear reactions will not be affected by temperature, pressure, or catalysts like chemical reactions will be. So we're going to be focusing on what's going on with the nucleus, not what's going on with the bonds between the atoms. Okay, so when an isotope is unstable, and when it has an unstable nucleus, it's called a radioisotope. And isotopes can be unstable because they have an unbalanced number of protons to neutrons. There's a specific ratio that makes a stable isotope, and we're going to get to that soon. But when it doesn't follow that ratio, when it's unstable, it wants to give off some type of radiation to become stable. And we're going to look at the three most common types of radiation, which are alpha, beta, and gamma. And here you can see we have a summary. So let's start with alpha radiation. What is that all about? So alpha radiation is composed of alpha particles, and an alpha particle is basically the same thing as a helium nucleus. It's 2 protons and 2 neutrons. And because it's 2 protons, alpha particles have a +2 charge. Alpha radiation consists of a stream of these alpha particles being emitted from an isotope. Now, because, relatively speaking, alpha particles are pretty big, they're not very penetrating, they're not very harmful. A single sheet of paper will stop an alpha particle. So alpha radiation isn't something that would harm you from the outside. Your clothes would stop alpha particles, but they could be harmful if you were to ingest something that was giving off alpha radiation. Or like when you inhale smoke, if you were to smoke, that could include radioactive material in your lungs. So we're going to represent an alpha particle like this right here, 4,2 helium. Now the 4, remember, is the mass number, which is protons plus neutrons. The 2 is the atomic number, which is the protons. And then we use the symbol helium because it's the same thing as a helium atom. It's just the nucleus part of it. Now, when you're looking at this as an equation, okay, you can figure out what these numbers and symbols are based on just very simple math. If we have 226 protons and neutrons, if we lose 4, how many do we have left? 222. If we have 88 protons and we lose 2, how many are left? 86, and element number 86 is radon. That's where the Rn comes from. So when you're writing these balanced equations, you want to look at making sure the top numbers and the bottom numbers are equivalent on both sides of the arrow. And we'll do a lot more practice with these. All right, let's talk about beta radiation. So a beta particle is going to be very small and very fast moving compared to an alpha particle. Beta particles are emitted when a neutron is converted into a proton. They have insignificant mass and they have a -1 charge. So we typically think about beta particles as being electrons. They do penetrate more than alpha particles do, but they can be stopped by a sheet of aluminum foil. Okay, so let's look at our balanced equation here. So we have iodine 131, and it is turning one of its neutrons into a proton. So the 131 part doesn't change, but the number of protons goes up. So the total is still 131. There's just one less neutron, one more proton. Now, this is the Greek letter beta. okay, we're actually going to use a symbol that is going to help us with the mass. We're going to use the symbol 0, -1, E, okay, rather than the actual beta symbol. So this is going to make the math work. 131 plus 0 is 131. 54 plus -1 is 53. Okay, so this is going to be our symbol for a beta particle. All right, let's talk about gamma radiation, which is the next one. So gamma rays are just radiation. They're not particles like alpha or beta, so they have no mass and they don't have any charge. And gamma rays are the really high energy that comes with alpha and beta radiation. They're similar to X-rays in their amount of energy, and gamma rays are very, very penetrating. That's what would be really dangerous from any sort of radioactive material.